Salam and welcome everyone. So today we're going to be working on the question on the screen that says for tetrachloromethane, the change in enthalpy of vaporization is equal to 30.0 kilojoule per mole. Calculate heat, work, change in enthalpy, as well as change in internal energy when 0.75 mole of tetrachloromethane is vaporized at 250 kelvins and 1 bar. The first thing you need to know is this. We've been given a question where we're told to determine heat as well as enthalpy in the same question. We have to understand that at constant pressure, heat is equivalent to the change in enthalpy. And we see that in this particular question, they did not tell us that the pressure was increased, it was decreased. They did not say the initial state was a particular number and then the final state was a particular number. They just told us that it's happening at 1 bar. So we can assume from this question that the pressure is constant. And because the pressure is constant, the heat as well as enthalpy will give us the same value. So what I'm trying to say is when we find heat, right, and we find enthalpy, we can simply, when we find heat or we find enthalpy, we can just simply know that finding one would equal the other. So that's basically what this is saying. Now, we're also told to find out work as well as change in internal energy. Note that by the time we determine the value for work, all we have to do is just remember that the change in internal energy is just Q plus W. So whatever the value for W is will be added to whatever we've solved for heat, and we will get the answer. So I just want to talk about the fact that this question should not scare anybody because it's a very fundamental question, and remembering the formulas that we've been using since we started this particular topic in physical chemistry is going to be the same thing you're going to be doing. So now, the only value we're given, right, um, aside from temperature and pressure, is the number of moles. So the values we're given aside from them are the number of moles as well as the change in enthalpy for vaporization. So the first thing you have to do is this. Remember that the units for heat as well as work is joules. So the units for heat, the unit for change in enthalpy, they are all joules, okay? Just joules. And this particular change in heat for vaporization is in kilojoule per mole. So what this is telling you is that enthalpy, okay, is just simply the change in vaporization for enthalpy times the number of moles. So this is what this is going to show you here. I'm just going to do the equation, and I'm only like breaking this down because I don't want a situation where people will be confused because they may be wondering like, okay, how did they go from here to here? So what I'm saying is the change in enthalpy is equal to the number of moles times the change in enthalpy of vaporization. Because if you remember, the unit for enthalpy or change in enthalpy is joules or kilojoules, okay? And then here is just simply the unit for change in enthalpy for vaporization is kilojoule per mole. So to go from the information on the left to the right, you have to use the number of moles. Or to go from the equation from the right to the left, you also have to use the number of moles. So in this particular question, we're just going to be multiplying the number of moles times the change in enthalpy for vaporization to get the change in enthalpy. So that's just how we're going to do. We're going to math it out. There's no major formula to go from changing enthalpy to changing enthalpy of vaporization. Just use the number of moles. So writing that out, we have changing enthalpy, which we're supposed to solve, is just the number of moles, which we've been told is 0.75 moles. Okay, remember that's what the question said, times the change in enthalpy for vaporization. So times 30.0 kilojoule per mole. So of course you cancel out the mole. So that would be 22.5 kilojoule. So that is basically the value or answer to enthalpy. And let's not forget, heat at constant pressure as well as change in enthalpy are the same value. So heat is therefore also going to be 22.5 kilojoule per mole. So yeah, that's basically what you do. If you want to stick to, yeah, that's basically what you do. That's 100% what you do. So we're going to stick to kilojoule per mole. We're not going to change it back to joules per mole. Doesn't really matter. That's just basically what we have. So the next thing we have to do is for us to determine work. Remember that generally the formula for work is negative P external or pressure, okay, that we're dealing with, times change in volume. But we also have to remember the chemistry behind this particular question. We're told that tetrachloromethane vaporized to go from liquid to vapor is gonna be basically a chemical reaction. So what I'm trying to say is to go from maybe having something in a container, which is in liquid form, okay, to gaseous form is going to look like this. Everything vaporized. So maybe if there's a hood in the lab, you see the volume goes from whatever is in this liquid to everywhere. You can see that the volume is going to significantly increase as it's basically vaporizing. So it's going to go everywhere. It's just like how water can be small in a pot, but when you heat it so much and it starts to vaporize, the entire room feels steamy. That's because the volume of water has left the water has left has vaporized from the pot to everywhere in the room, and you can see the volume increases. This is the reason why you feel this steam all over, even though it might just be a small portion of water. So what this is telling you is this: that since you have this information, you cannot look at volume in the same way anymore, because the volume of the gas, right, has become significantly greater, right? Significantly, like much, much larger than the volume of the liquid. So than the initial volume. So the final volume of the gas is significantly greater than the initial volume of the gas. So knowing this information, we understand that the final volume is going to be approximately the change in volume. It's just like, say, the volume of the gas before, sorry, the volume of the liquid before, say, initial volume was 5 milliliter. And then all of a sudden it goes from 5 milliliter to a million, okay, milliliter. Well, if you want to do the math, you would see that the final volume, which is here, would be significantly, meaning 1 million millimeter is significantly greater than 5 milliliter. So, what this is trying to tell you is that approximately the final volume is the change in volume, and we can represent this mathematically as rewriting. Basically rewriting the equation. So we end up having work done equals negative P times V final. So this is basically what we end up with. So that's going to be the one that we're using. Now, we go back to our question. We remember that we're given pressure, right? 1 bar, but we were not in any way, shape, or form given the final volume. So we remember that the common formula that we started when we started with PChem is PV equals nRT. So since we don't know what the volume is because we're not given the initial or final volume or any volume, we can find whatever the value of VF is, but in terms of other parameters. So that means V here is now going to be nRT divided by P. So basically that's just going to be what we're going to input. So rather than having W equals negative P VF, we're gonna have W equals negative P, so times nRT divided by P. Well, the pressure remains constant, the same value, so we can just simply cancel that out. So pressure cancel. So really work done ends up becoming W equals negative nRT. So what else are we going to do? We're just going to substitute. So W equals negative, what is the number of moles that we're given again? 0.70. Sorry, 0.75. So 0.75 mole. We're told the number of moles. Sorry, the gas constant. We've been told the number of moles. So next we move on to the gas constant. So that will be 8.3145 joule per mole. Kelvin, and we've been told the temperature. If we go back to the question, we see temperature is 250 kelvins. Okay, so 250 kelvins. So of course, we do the math, cancel out of the units first, cancel out the Kelvin, the number of moles, and we just multiply. So that will be W equals negative 0.75 times 8.31415, right, times 250, all of that joules. So W equals negative 1558.969 joules. So that's basically what's going to be the answer right here. So of course, because we want to clean up our work, we can just do this in kilojoules, right? We can also determine the value in kilojoules. So that's going to be W equals negative 1.55897 kilojoule. So that's how you do it. Now, let's not forget that the change in internal energy, which is the last thing we're asked to solve for, is Q plus W. So going back to the question, you see that we're also asked to determine the change in internal energy. So we know that's Q plus W. We already know the value of our Q. which is simply 22.5 kilojoule per mole, as well as the value of our work. So we're just going to substitute. So you have change in internal energy equals 2 22 sorry, 0.5 kilojoule, okay, plus minus negative 1.55897 kilojoule. So when you do this information, we end up getting 20.94103 kilojoule. So of course, we're given our initial question. We're given three sig figs for the change in enthalpy of vaporization. We're given three sig figs for number of moles and three sig figs for the value of temperature, and we use all of that information. So we have to put our final answer in three sig figs. So the change in internal energy becomes 20.9 kilojoules. So this is basically the answer to this question. So hopefully I've been able to break down this information in a way that you're going to understand. There's also another video that is going to be posted on my channel for another question using the same information and same format. So make sure you watch that video as well. If you have any questions, please put it in the comment section. If you would like me to be your personal tutor, I help students who want to succeed in all their chem related subjects to succeed in all those chem related subjects. If you'd also want me to be your school mentor, I'm an educator, mentor, as well as tutor for students in middle school, high school, as well as college for all their STEM related courses. So make sure you email me at shohabitutoring@gmail.com. And if you also just want a coaching session as you're about to resume school or as you're about to take a test, please make sure you email me at shohabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.